So I'm going to explain. So supersonic flow through a CD nozzle using Ansys discovery. So I'm taking the rectangular duct CD nozzle. So I'm assuming inlet outlet area is 1 meter square. That means 1 meter height, 1 meter width, that is unit span. So I'm taking 2D model, so both side 1 meter, and if you are taking just a symmetrical model, axis symmetrical model, then it is just 0.5 meter and 0.5 meter on both sides. And using isotropic calculation, so we can find other properties. For example, I am fixing P0, T0. Stagnation pressure temperature is 101325 meter square and temperature is 300 Kelvin, and I am simulating the exit Mach number of 3. So for that Mach number 3, so I am using isentropic table to find other properties. For example, so static pressure at that station is 2758 Pascal, temperature is 107 Kelvin. In the same way I can proceed for the what is the area in the throat, that is 0.118 meter height. And the inlet also I got the what is pressure and static temperature. So with this I am going to proceed for the simulation. So I am taking this kind of just a CD nozzle. Both side I am taking angle as 15 degree. Small curvature I have given in the center. So now we can go for the Ansys discovery. So this is the main window of the Ansys discovery. So already I made the CATIA file, so I am going to load it. So use insert geometry from the main menu, and I have saved the file here. CD nozzle for 500 mm, that is both sides of 500 mm. So this is the object. Just a double click in the window. Using by holding the scroll button, you can rotate it, or using this views, you can put it in the proper view. So next step, go to the simulation. There you can define all the boundary conditions using this fluid flow. So before that, let me define the material. So this is not the aluminum, this should be air. So double click this, you can expand. So I am taking air, any air you can use it. So air is selected. Then I am going for the fluid flow to define the boundaries. So this is my inlet. So not the velocity, I am going to define as the pressure. And pressure value already we checked in the PPT, it is 99977.38 Pascal. And the temperature also we found in terms of Kelvin, it is 298.86. Kelvin. So inlet property I have defined. Then I can define the outlet. Just rotate, select this, change it to outlet, and here pressure is 2758.07 Pascal, and the temperature is 107.13 Kelvin. So you can cross check it, 107.13 Kelvin. So both sides I have defined. Then I will define this top as a static wall, that is not slip. Actually automatically it is taken all the side as a wall. Okay, as we defined the inlet and outlet, now it is taking only the other thing as a wall. So I am going to use symmetry on both sides. Okay, first this side, next opposite side, then this bottom line also, because I am not taking the full model, I am taking only the one off. So this is also symmetry. So only top one is the wall, this is the inlet, this is the outlet, remaining and all symmetry on both side and the bottom. So I have defined all the boundary conditions. So whatever we have given is the for the incompressible. To change this to compressible, double click the air, you can see this symbol, click this to change this to the compressible, so that now you see the operating pressure. Okay, so I am going to change this operating pressure and temperature to the outlet, so that flow will be the properly expanded for the design condition. So I know the exit pressure, I got it as 2758.07, 2758.07, and the exit temperature, it was 107.13 Kelvin. So I am giving the same pressure temperature outside, and that it is operating like that I am giving. So now we can simulate. You can see the contour. So in the velocity, instead of velocity, you can check the Mach number. So I have designed for Mach number 3, I have given boundary conditions for Mach number 3, it goes up to 2.98. So if I refine the mesh further, it may be further moving closer to the Mach number 3. So you can see this yellow color shadow rotating, that means the simulation is still going on. Now it is finished. So I achieved maximum 2.98 instead of Mach number 3. This is the isometric view. You can check the other views also. And if you want, you can refine the mesh also. This is the plane that we can use it for view. So go to design, use this move button to move any planar object. Select this. I'm going to rotate this plane to 90 degree. So now this is the mesh it was used here. So if you want, you can refine further using the simulation tab. Locally also you can refine, or globally also, instead of this custom. By increasing the number, you can refine it. Yeah, that's it. If you want, you can see the other properties, Mach number, then how static pressure varied, how density varied, all those things you can see here. Yeah, that's it.